Last one of the sittings. Sean misses it.
Sounds like an exciting game. All right. So, hi folks, and welcome to another SPETT technical session. My name is Xavier Moonan. I'm the program chair for the SPETT. And yeah, first off, we'll kick off with some of the events that we would have had over the past couple months. So you can see there's a whole range of topics that we would have covered. We would have had like a distinguished lecturer speaking about decommissioning. We touched on managed pressure drilling. We looked at the SIP field and its subsea design and development. The decarbonization of the Zambezi offshore platform. We looked at the story of Cascadura. That's the onshore gas field. And then we had a in-person presentation at Tucker Energy with dealing with wellbore construction and cementing. We had the CBAM, Carbon Border Adjustment Mechanism, being discussed by Prof. Donny Goodall. We chatted with CEO Candace Longchi from CSA Ocean Sciences. And last talk that we had was by Juan Pablo Francos from DNM, talking about classification and categorization of petroleum reserves and resources. So today, I'm going to give I consider it an introductory talk into key areas across Trinidad and Tobago, and then trying to help people understand like how everything kind of came together. You can feel free to leave questions in the chat. And coming up in the end of June, we will have a in-person, a physical tour of Deca Petroleum bitumen processing facilities. And that's actually located in Point Lisas. They will be hosting us there on 26th of June from 1:30 to 3:30 p.m. So you'll see that ad coming out shortly. So sign up for that. Coming up in July, we'll then have the Mature Basins Energy Symposium. I'll talk a bit more on that in a bit. And that's a pretty interesting big event that we're having this year. Later in July, we then have two talks, one on PCP systems on the 16th of July, and then one on GIS, geology to GIS in the 31st of July. So here's our symposium that I talked about. So the Mature Basins Energy Symposium, really it's geared towards highlighting some of the, we are a mature province. We have been producing hydrocarbons for quite some time. I've been told instead of using 168 years of production, we should actually check all the way back to when Sir Walter Raleigh came here and started using some of the oil standards so would fix his ships, which would add a couple hundred years to that, right? But as a mature province, we have mature areas do have a lot of challenges, and we're seeing more and more of those challenges. But there are a lot of opportunities too. So all of these companies stuff have been working in this basin, and everybody has good ideas and have tried different things, have learned from lots of trials. So let's share some of that and let's learn from each other so we could continue to find and develop this area and make it efficient for hydrocarbon extraction. So we will have 3 distinguished panels in this symposium, and we will have 5 high-impact technical sessions, and we'll have 2 pretty good luncheon talks. You don't want to miss this. Many thanks to all of these companies who are current sponsors of this project that we're having. So our only symposium for this year. Maybe we'll have more next year. So like I said, 1st and 2nd July, Cara Suites Hotel. You will see the program dropping really soon, early next week. And from that, we'll have the commencement of registrations for this program. Looking forward to seeing you all there. All right, so talk for today, I'm gonna, like I said, gonna be talking about the general geology and geography of the Trinidad and Tobago area. Um, and and I know some of these are going to touch on some key sites across these two islands. And maybe some of these sites you're familiar with. Hopefully at the end, I'm going to basically show how all of these particular sites that you might go and visit now, how they all kind of came together to form these two islands as they are now. My background, I'm the exploration manager at Touchstone Exploration. I've been in oil and gas for about 20 years now. I started off in mud logging and geoservices, and then I moved on to Petrin, state company, then on to Centrica, a British company exploring on the North Coast, and now I'm at Touchstone. I've also lectured at the University of the West Indies for quite some time, and I love to teach people about field geology and get folks excited about what we can do and what we can explore for in this area. I've helped bring together a bunch of conferences, both from the GSCD side and the AAPG side. Um, I'm not a petroleum engineer, but I've actually found it really interesting to work with engineers. And so I've become part of the SDE, and now I chair the program section of the SPE, Trinidad and Tobago section. Yeah, so let's go. Okay, so here's a pretty nice image. I love overlaying, surface geology on topography and just like looking at it from different perspectives and stuff. This would be the LATNA surface geology map. It's a revision to a pretty good revision to the original Kugler 1959 surface geology map. And I must say, real comment, kudos to Google. Like very little really has changed over much of this map. It's been slight tweaking and stuff here and there in later revisions. So always looking at things in different perspectives give you, different ideas. So if you're gonna explore the area, let's learn a little bit about the topography and stuff of the area that we sit on, right? Um, you all would know that Trinidad obviously has three ranges, right? We have the Northern Range, Southern Range, and the Central Range. And those ranges basically run, west to east or southwest and northeast across the islands. And that's kind of highlighted here, all the warm colors, all the high areas and stuff, right? You could see that also, with the tightness of the contours, continues into eastern Venezuela. Here's the Paria Peninsula from Venezuela side, and here's the Gulf of Paria, right? Um, and the central range area, you can see that high actually also extends further off towards the east coast, where we have like shallow areas like called the Emerald Shoal and stuff, in vicinity of like where the Angostura gas field and stuff is. As you get out towards the further towards the east, you can see the tightness of some of these contours. And so there's a significant drop. That's your slope setting there as you head out into the abyssal plain, becoming part of the accretionary prism to the north where Barbados and stuff sits. Here we have Tobago, pretty simple, nice southwest northeast trending ridge. And you have tight contours towards the east as well. We have a ridge continuing, that Tobago's ridge continuing a bit towards the east as well from there. And on the north side, we're pretty, the spacing of these contours tell you that it's pretty gentle, right? Very, very gentle change in gradient across this area. A very broad, stable shelf, where we would have series of gas fields. And then as we go towards the Tobago area, we see some of those contours that are tightened. And that's where we have the North Tobago fault, which is a very tectonically active area. We still have earthquakes on it today, and some of the big earthquakes in the past occurred along this area. So that really is a fault control shelf edge on that side, right? Okay, so that's topographic highs and stuff, right? Obviously, if you're searching around for hydrocarbons and stuff, high or highs or and declines are usually a go-to place to start the search. What about the basement? So how did we form some of these highs? What about the underlying fabric? Is it trending the same way? Actually, it does. It does trend pretty similarly. On this map, this is a magnetics map across Trinidad. It's a topography map over Tobago still, right? This magnetic map is highlighting really linear. You see lots of linear trends, southwest to northeast trending features across, especially southern Trinidad, right? And that lines up quite well with some of the features even running through the central range. Note that, the features are, yeah, yes, they're generally trending southwest to northeast, but they're also in small groups, right? You could connect the dots, but maybe why are they dots in the first place? Might be a question. Are there breaks between some of these features? Right. So as a trend
545.
southwest, to northeast, are there then breaks then that split up these features, right? But you see that dominant sort of trend like that. You also have some features that trend like northwest to southeast across the area too, right? And so maybe I'll just throw this out here. So it was postulated that the topographic highs which occur on the south side of the country in what we call the Trinity Hills actually what gave the name to Trinidad in the first place, right? Um, the thing is that Columbus was actually approaching the islands from the east, and more than likely, he actually saw the northern range, the central range, and southern range, forming three sort of peaks in the horizon. And that may have then given us that name, La Trinity. Slapping on the surface geology now, we have mostly metamorphic rocks, low-grade metamorphic rocks in the northern range. We'll start to look at some of those a bit more. The eastern part of, sorry, the eastern part of the northern range, the coastline is much smoother than what you see on the western side, right? It looks a bit, indented, almost as if you're taking the area and pushing it down and drowning the base, right? So there's a big change occurring right across what we call this hinge point at Lafayette, right? On the Blanchisseuse side, the bays are a lot gentler and they don't indent into the mainland significantly. Yeah, again, the surface geology matches very well with the topography with the basement rocks as well, showing that most of the folds trend southwest to northeast. Pretty glaring example is like this rock dome anticline, which occurs over here. And it trends southwest to northeast. We have the David Wellington structure, southwest to northeast. Forest Reserve anticline, southwest to northeast. You name it, right? They're all trending about that. Um, we we understand that we're in a fold belt, and I'll show you what that means. So the rocks are being compressed significantly. And what that means is that we have tighter folds towards the central range area and broader folds to the south as the fold belt dies out towards the hinterland to the south, right? Towards Venezuela. So we have tighter folds in the central range. And then as we come out to the southern range, these folds are broader and broader. Okay? So back to the perspective, just to add some context to the colors for the surface geology map. We could start here at San Fernando Hill. San Fernando Hill is being shown with its green color. That's our Cretaceous rocks. So they're like 65 million years old. They also serve as the soft rock when buried deeply in the basin, and they expel. That's the rock that expels the hydrocarbon in the basin. So high carbon levels in those rocks, and when they are placed in the right temperature and pressure window, they expel hydrocarbons. The type of hydrocarbon will also be related to depth and pressure that's been applied, and also the actual um, makeup of the rock itself. Is it rich? What is it made of? What sort of kerogens are present in it? So going from the north, we got the metamorphosed Cretaceous and Jurassic rocks. Allochthonous, that's a nice fancy geological word for far travel. So it came from far away, right? Whereas the stuff at the south side of the country pretty much was here all of the time, meaning it sat just north of eastern Venezuela, right? Northern range was not necessarily here. So it came and met some of these other areas. Then we have the central range, which has the fold belt that I was talking about, in the river fold and thrust belt. So lots of compression going on inside here. But while the compression is occurring inside this area, the area between the northern range and the central range is what we call a passive deltaic piggyback basin, meaning it's filled up with deltaics, delta deposits, sands and shale sequences, and they sit on the back of this area that is being compressed. So the area is being compressed outward, and this is sort of like getting a piggyback ride along with the compression, right? So just sitting on the back of it, and it's not being compressed on this side. In fact, there's no significant compression ongoing in this area. It's mostly extension or normal folding. As we go to the south side, the fold belt, like I said, continues all the way to the south coast. It You're getting broader and broader folds as we go further towards the hinterland. And into this area, we also have the big deposits being deposited on top of and covering some of these folds or burying some of these folds, right? And so most of those rocks are ranging from the late Miocene all the way to, so that's like about 8 million years ago, all the way to the Pleistocene, 2 to 1 million years ago. So we would have had deltas flowing through this area, filling up these basins. But they would have filled up a very passive basin to the north, and they would have filled up a basin that was folding actively to the south. So even though we had delta, branches of a delta flowing into here, still different things were happening in the northern area versus the southern area. Okay, so here, this is like a one slider, sort of trying to explain the whole evolution of the Trinidad area. Um, I would have shown some of my students during the courses in UE. Let's go through each of these images here slowly. So let's go 255 million years ago, right? So 255 million years ago, right? As you can see, most of the continents were all together, right? And they would have formed pretty much the larger continent, which was referred to as Pangea, right? You can make out the outline of South America and Africa, and where Florida sits in that depiction there. Essentially, Trinidad would have been right where I've got my red laser pointer there on. You've seen that, right? And pretty much that means we sat near center of this continent. So the area was really different. Most continents these days, at the center of these continents, you actually have desert condition. You could have swamps in some places as the area starts to break up, but we believe that it would have had predominantly arid conditions in this area. So imagine if you were able to drill down to the Permian in Trinidad, you probably would find some Aeolian sandstones and stuff. But following that, from 255 million years coming up to 154 million years ago, right? Here's a close-up now of where Trinidad would have sit. Note that this is the actual shape of Trinidad now, but that's not how it would have been shaped then. Generally, southern Trinidad would have been sitting where my red pointer is there. And so just to the east of us would have really been Cuba, the area that becomes Cuba, and the Bahama platform, the Bahama Islands, and Florida, right? So just to the east of us would have been that. And then further to the south of us, we would have had Guyana, Suriname, that hasn't changed. They're right there. And further to the east of that would have been the Guinea Plateau and basically the western part of Africa. So what would have happened was that this area started to tear apart, right, with the Central Atlantic opening starting in the northeast, coming down towards the Guinea Plateau area, and then that would have wrapped around at the Demerara Plateau. This area over here begins to move generally towards the northwest, right? And as it moves towards the northwest, essentially you could picture it as the area that becomes Cuba moves away from the Demerara Plateau, and that creates a basin. That is the birth of the Guyana-Suriname basin. That Cuba landmass moves along what is called the Guyana Transform Fault, taking it past Trinidad, what would have been Trinidad, and then the opening of the Caribbean area kind of started from that point. So we would have then started to open this area, this deltaic opening from the east to the west towards Colombia. And that opening would have led to the eventual creation of the Caribbean Sea area, right? So we started here, we ripped this down and then basically pulled this back up this way, and Florida, Cuba, everything just moved past us away towards the northwest. So when this opening was occurring, you create lots of normal faults. If you're basically pulling an area apart, stretching it, you're extending it, you're going to create lots of normal faults. And that's what's being depicted in these little cartoons. This is south, and this is north, right? South on the right. And we basically come from the South American continent and we create a staircase, stepping down towards the north. I got some labels up here. Generally, PRF is like Point Radix fault, this is Los Bajos fault, and the Southern Range fault, and Central Range fault. And so we're just generally saying that as the Trinidad area stretched, we created a staircase that stepped down to the north, right? As we step down to the north, of course, this is not happening above sea level. This is all below sea level. And so as you create space, sediment is going to then have an area to infill. So following 100 million years ago, we would have then continued to infill the area with sediment. These areas would have continued to extend and extend a bit, and that created more and more space for sediment. So I'm showing some yellow blobs over here where sands and stuff might have been funneled into and deposited. The world started really to change. Trinidad area, that is, started to change from about 25 million years ago. So on this little map here is southern Trinidad. Northern Trinidad is still nowhere to be seen on that map. What started to happen here was that the area began to be compressed. And it was being compressed from the north to the south because of the Caribbean plate that was moving relatively towards the east. So basically, the Caribbean plate was behaving like a bulldozer coming from the east, coming from the west to the east, and influencing all of the rock and the faults and the fault fabric of this area. So we had normal faults, as you can see from the arrows before, they're all pointing down, showing extension. But then later on, we just started to compress that. And what happens with faults is that it's a weak zone. It's a break in the rock. So if you apply a different stress to it, chances are that same weak zone will be reutilized, but maybe in a different way, depending on which direction you're applying the stress. In this case, the stresses were basically being applied from the north to the south, compressing it. So what was once a deep basin or a deep graben then starts to become a folded hill, right? So it starts to sort of then be pushed back up. So we call that inversion. So we're pushing it back upwards now. So it used to go down, now it's going back up. And that started the full belt story for Trinidad. As this area was being pushed up, um, it, it, it created high areas and new low areas. And into those low areas, we would have the sediments being diverted to. The high areas, if they did pop up above sea level, they would then be eroded, and some of that material might then be reintroduced into the new low areas to the south or to the north. Okay, so let's look at a couple key features around Tobago and how does Tobago fit into this whole thing. So this is probably a view or vantage point that not many people would normally have, all right? This is Toko sitting out over here to the right. And here is, yeah, well, it's like Store Bay, Pigeon Point and stuff in Tobago, right? So we're looking at it from the perspective of from the northwest to the southeast. Like I said, we're going to compress this area. But what is actually happening in the Tobago area, where this area sitting out here below, this is actually the basement rocks, or the same rocks that are related to what we see on Tobago, right? The basement rocks, they're not exposed. They're covered by thousands of feet of sediment now, but we can use seismic data to map the basement, and I'll show you what that looks like in a bit. But when we map the basement, we see a lot of interesting features on it. I've just drawn onto here where some of the key faults are, and also put on where some of the key earthquakes would have occurred. And they occur along these faults, which literally form huge staircases, right? Like a huge step, thousands of feet of slip along them, right? And those are the steps that are forming the North Tobago Fault. On Tobago, we have a range of volcanics, right? The Tobago volcanic group, where you have diorites and gabbros and stuff. So you could see those, especially about like Argyle waterfall area. And then if you go on the north coast, on the northern coast or northwestern coast, so sorry, northeastern coast of Tobago, like at Englishman's Bay, coming along there, you would have a lot of what we call the North Coast schist group or green schist patches. Essentially, they're volcanic plastic rocks, so rocks that were eroded from the volcanic rocks that got redeposited as sedimentary style rocks. They also got metamorphosed by some of the volcanics, right? And then sitting out over here further towards the southwest of Tobago, you then have the very young coralline limestones. Below that, you also have some evidence of sandstones and stuff. All of the basement where it has been drilled to, right? So we drilled down into this and sampled those rocks, and they're all either metamorphosed volcanic rocks or metamorphosed sedimentary rocks. That's what we tend to find when we drill out in these areas. All right, so I've highlighted onto this map a bunch of areas that we're going to like take a closer look at, right? And I think we're going to start off in the Tobago area. So we got like Rockley Bay, Plymouth, Englishman's Bay, and some place that I named Isla de la Asunción, the Hinge and the North Tobago Falls, which we saw a little bit just now, and then the North Coast biogenic gas fields, which have been talked about in the media quite a lot recently. We'll then fly over to Trinidad and look at Turure area, Caroni Basin, Piparamid volcano, San Fernando Hill, Pitch Lake, the Southern Basin itself, the Palmis Pool Bed, Salt Spring, and Los Iros. And then we'll see how this all looked like hundreds of millions of years ago and then bring it all together to present day. So, okay, so back again at the North Coast area. Um, so here's the Dragon gas discovery, right, which sits over here. Been part in the media a lot, so now you can see exactly where it is. Here is our maritime boundary, right? So it sits right at the edge of the boundary. Quite interesting, right? That the gas field stopped at the boundary. Quite convenient. Anyways, here's the hibiscus and the poinsettia and chiconia gas fields. They're all biogenic gas fields, meaning that the gas there is actually being generated from microbial bacteria that's breaking down the small amounts of carbon that's stored inside some of the shales inside the deltaics here. Um, there's actually quite a lot, so it accumulates. And the good thing is that, well, gas tends to obviously float on water. So any of the salt water that's trapped inside of those sandstones, the gas basically goes to the top of that. And in this area, there's actually a ridge that runs from the Patao area all the way through from Dragon, Hibiscus to Orchid. And that's the broad shelfal area that I was talking about. But sitting below that broad shelfal area is actually a structural high. And that bump basically allows the gas to migrate and accumulate and focus towards the top of that bump. So it focuses all of that biogenic gas into these areas, creating these pools. And in some cases, there are multiple levels of these pools. So in the hibiscus poinsettia area, for instance, the poinsettia sands are shallower. Then you have the hibiscus sands a bit deeper, and the chiconia sands a little deeper than that, like for example. Yeah, so that's what we got there. You can also see in this picture the western side of the island around Port of Spain over here. Like I talked about those coastlines. This western area is actually going down, while the eastern area is actually coming up. And that's why some of these coastlines here have that sort of jagged or indented nature to them, right? So we're literally drowning these former valleys. Um, so this area may have looked like this coastline might have looked more like the Bangladesh coastline back in the past, but it's now going downwards. Obviously, we have a lot of drowned valleys already completely drowned, which then creates down the islands sort of areas, right? All right. So here's now. Let's take a slice through the area. So here is what we call a seismic line. This seismic line runs from approximately offshore Lafayette, Blanchisseuse area, running towards the Orchid gas field, and then towards the Iris gas discovery, up towards Castra gas field, and then up towards the northern east side of Tobago. And what are we seeing here? Relatively at the top here, this first this first bright surface that you're seeing, that's the seabed. So the seabed is pretty shallow in the areas to the southwest of the line, and the seabed gets deeper towards the northeastern part of the line. This vertical scale is actually in feet, so we converted it to feet. Seismic is normally displayed in time, but if you have enough data, you could convert it from time to depth. So in this case, it is shown in feet. And so you can see that the seabed way out in the deep areas of Tobago exceed about 2,000 feet water depths, right? Whereas most of the seabed along the broad shelf is sitting in less than 200 feet water depth. Okay. Okay, so we got lots of layers. Not much folding, but we can see some pretty distinct breaks, right? Try to just correlate what might have been joined to what at some point in time. There's definitely some breaks running through this, right? And those would be faults. So here we have a series of faults stemming from the basement rocks. So the basement is also showing a very bright amplitude down here. Basement occurs at 10,000 feet out over here, climbs up to as shallow as 7, drops down 1,000 feet, and then keeps going again. So that's the North Tobago Fault, which basically is the reason for the areas further north of Tobago being downthrown even deeper. We also have lots of nice interbedded layers. We see like lines of stripy nature to the seismic, and that suggests that you have interbedded sands and shales. A lot of changes in the type of the rock being deposited, right? So layers of sands, layers of shales. It's always constantly changing. After about this point here, we then have a pretty washed out sort of zone. It looks whitish, sort of, right? So there's less of those changes. It's mostly one type of rock type that's occurring inside there, more homogeneous, right? And so we got like mostly deep water muds inside here. And then you got a few of these bright blips sitting inside here. And in this basin, these bright areas are usually gas charged sandstone. In this case, these are bright gas charged sandstones sitting inside these deep water muds, and they're actually a turbidite deposit, right? So they're a deep water sand. Came off the shelf under some extreme conditions, and the sands ended up way out into the deep water area. That's like taking sand from Blanchisseuse and throwing it all the way out to the northern parts of Tobago. It's quite a long distance, but it is possible according to the slope. Get these sands to get out there. Sitting out over here is another gas area, right? Gas rich area. This is on production right now. That's the Castra field. And those are shelf full sands sitting inside there that are charged up with gas. The basement is quite interesting. It's very jagged in some places, right? And so what we would have done here was we actually mapped out the basement, and we noticed that some of these jagged patterns actually had a lot more interesting things to them than we thought. When you look at the basement from above, after mapping it out across Tobago, so here's the Tobago Fault, which is down showing this area to the north. And what we saw were lots of drainage patterns, right? Even meanders within these little valleys, dendritic drainage, lots of it, all over, right? Even further south over here towards Tobago itself, lots of drainage. And it suggests here that what we know as Tobago today wasn't necessarily how big Tobago was in the past. Tobago was actually much larger, right? And may have had a sort of sister island next to it, which is no longer above sea level. And that island had rivers on it. It also had high points. The highest point in Tobago is called Pigeon Peak. And this island also has a really high point. I'll show you that in a bit. But where did Tobago come from? And is Tobago actually related to Trinidad? Not really, actually. So Tobago actually was sitting within an arc. So here is South America. Here is North America. And this area further to the west would be the area that eventually becomes the Caribbean plate. But sitting in front of it was an arc. And within that arc, we had the Greater Antilles, and we had Tobago in the middle. Then we had like Bonaire and Curacao and Aruba, those islands, right? And pretty much Tobago is expected to have been at near mid of that arc, near the middle of the arc. Essentially, the Caribbean plate then comes through and sort of breaks that arc or ruptures that arc into two. And as it breaks, the Greater Antilles are then pushed against North American plates to the north, and the Southern Antilles, Borneo, Curacao, and Tobago, basically get pushed against South American continent to the south. And Tobago, having been in the middle of this, basically ends up being on the most eastern part of South America when it gets plastered onto South America. As the Caribbean plate then comes into the area, bulldozing its way into the area, it basically pushes Tobago further and further east. And so Tobago ends up the island that was at the center of that arc ends up the most furthest east over time. So this is what we think Trinidad and Tobago and Isla de la Asunción may have looked like in the past. So here's where Trinidad and Tobago sit now, the green demarcations there. But about 6 million years ago, this is where they may have been. And most of them would have been above sea level at that point in time. After 6 million years, the Isla de Asunción Island would have begun to sink because of the movement along the North Tobago Fault, dropping the area in the north downward over time. Right, so we have Pigeon Peak, which is at 550 meters out in the near Speyside area in Tobago. And similarly, the highest point in this island, I named it Mount Cruna after my wife. It's 524 feet, 24 meters from where we picked up most likely was the edge of that island system. Right, so that's what Tobago may have looked like and its sister would have looked like back then. Other things about Tobago. Well, if you go to Englishman's Bay, which is on the north side of Tobago, you'll see some of your metamorphosed siliciclastic and volcaniclastic rocks. So here you have layers. Yeah, we have layers and layers of eroded volcanics being redeposited and folded, and the multiple phases of folding. So if you ever go to Englishman's Bay on the northern side of Tobago, yeah, I know most people when they go to Englishman's Bay, they just watch the water, right? What's straight ahead of them to the north. But if you just turn around and look at some of the rocks behind, you'll see some really fantastic folds sitting in those rocks. And most of that layers and layers of volcanic classics that have just been folded over time, right? Other things, as you travel down on the northern side of Tobago, you may go to Plymouth. At Plymouth, there's some really distinct rocks there that a few folks may have like taken pictures and sent to me and be like, hey, what's this, right? You see these really nice light colored rocks, which are called tonalites. And then you have these very dark, very distinct, very dark, blackish in color, grayish in color rocks. And they're very linear, right? And they are called mafic dikes, right? So dikes, they're basically intrusions from deeper volcanism, right? So you would have had your tonalite deposits across the area, and basically during a period of volcanism, in this case, it would have happened during the Cretaceous time. Tobago was a volcanic island back then, and any fractures would have allowed for the dikes to basically intrude and basically flow through that area. So they occur very linear because of the nature of fractures. So they're basically infilling these fractures quite actively from the volcanism. And that's how you end up with those dark mafic dikes and basically sitting adjacent to something that's completely different from it. Jumping to the south side, we have our siliciclastic rocks. So here we have barnacle beds, and they're not modern barnacle beds. They're actually about a couple million years old. So it might be you might think that they may have been barnacles being growing today, but they're actually from there from a long time before. So this is near Rockley Bay in Tobago. So there's a nice little exposure right at Rockley Bay itself there, and you get these uh um the bananas bivalves, lots of gastropods. You get lots of fragments of crabs. We've also found shark teeth in this area as well too, and they're all dating back to the Pleistocene period. And some of these are in growth position, and some have been like eroded and collapsed and redeposited. So putting some of that into perspective, here's like the Rocky Bay outcrop to the south, and then here is like the Store Bay, Pigeon Point area with limestones near at surface, right? And some of those, the brown area is volcanic rocks. The red area is the igneous rocks, which sit below the basement rocks. And that extends offshore, and the sedimentary package thickens offshore. And that's what people drill for offshore, sitting inside some of these same plastic rocks, which are of the Rockly Bay age, sandstones and turbidites. Okay, so a bit of Tobago. Let's jump to Trinidad. No better place to start than at San Fernando Hill itself. It's a really great vantage point. It's used as our country's mapping data as well too. So it's a pretty good point that you could actually pick up and see or survey um, from practically every direction in Trinidad. So it's about 200 meters high. That's a nice rock face exposed there. It trends west, southwest, east, northeast, which is the same trend of many inclines in the country. These rocks, like I said before, they're Cretaceous in age. So they're some of the older rocks that we have exposed, ranging from 73 to 93 million years old. And a lot of these rocks are from the upper slope to shelf-fall environment, right? A lot of the rocks exposed here, you get a slight lightish brown colors when they're weathering. And many of those are like marls, right? They're very much rich in calcium carbonate, but there's also a lot of siliceous material in there too. So we find chert as well. And in some of these calcite veins, here's a piece of rock from San Fernando Hill. Get lots of calcite veins through it. And sometimes inside those calcite veins, you also have oil that was being generated from the rock or even from deeper parts of the Cretaceous rock is now being trapped in some of the calcite. So from north to south, here is the Caroni Basin, the Central Range, the River Fold Belt, and then the Fold Belt continues into the Southern Basin. Like I said before, the Caroni Basin is a piggyback. So you have this Central Range being pushed upward and pushing everything southward. And this area is accommodating sediment. It's not being folded, and it's actually just riding on the back of the advancing fold belt. The fold belt is pushing and folding the rocks. You can see these are really nicely creating hills, subsurface hills and stuff down here. And then following the yellow layer, we then have infilling of the basin, covering some of those hills, burying them, right? So we'll traverse some of this area. So let's go to the north side, Caroni Basin. The Caroni Basin here is approximately Freeport and Chaguanas, right? Long Denville sitting there, right? And we go all the way up towards Mahaica to the east. So this line is running like southwest and northeast across the Caroni Basin. Right, so you have west to east here. And again, just like the North Coast, you can see lots of nice layers. not much folding per se, lots of layers upon layers upon layers, right? There is a lot of interesting stuff going on down here, but relatively you can see some nice clear breaks where faults probably are, and some odd bright spots as well too. What are those? So we got lots of nice normal faults with the air collapsing, and we have some gas sands. So yes, and of course, in the Caroni Basin, there is a gas field called the Mahica gas field that's sitting out here, close to this well named M2. And yeah, it produces biogenic gas from the Durham sandstones in this area. And sitting even deeper down, there are also some other bright areas as well too. Not much seismic across this area, but interesting that there is a gas. Going a bit further north into the northern range now. In the northern range, a very popular spot is called Turure. They're locally called the water steps, right? It's a nice, easy hike. I've taken my 3 hour on that. And so you start the hike down at the base of the river, basically hike up parts of the river and along the river. And eventually we get up into where some of these streams feeding the main river, they enter areas where the quarry limestone actually occurs at surface. So this is a meta limestone, metamorphosed limestone sitting up here, naturally up here. And these are lower Cretaceous to Jurassic in age, right? And so they were deposited in shelf setting many, many millions of years ago. So they were deposited, then folded into the northern range and exposed. And when the water basically starts to erode into these and dissolve these, it basically makes this river water super saturated in calcium carbonate. The other rivers are not necessarily being fed by that. So there is an actual point on the trail where you'll actually go from, you'll see two rivers, like a split, a Y in the rivers, right? And going up one river, you'll see evidence of limestone deposits. And going up the next river, you'll not see that anymore. So when that water basically comes down the river, every time there's an abrupt change in the stream gradient, you get a bit more of oxygenation occurring, and that allows for the microbial bacteria to basically start to break down some of the deposits in the water and help precipitate this limestone. So the limestone that's actually being precipitated and forming the water steps are actually called tufa deposits. All right, so there's a perspective, and we have the Hollis Reservoir sitting here, the stream going up to Kumaka, that's where the limestones are. And we have the water steps forming along the way, usually associated with local faults. Right? Here's what the tufa limestone looks like on surface from above. They sort of look like they grow outward over time. All right, going southward now to Piparo. That's a popular one. Piparo mud volcano basically sits in the Central Range area along a fault called the Naprema Trust. So the same fault that's basically helping push up the Naprema Hill and basically popping it upwards. That fault basically makes a left bend at the Piparo mud volcano area. And what happens there is that it applies localized compression to this area. So here we have the San Fernando Hill area, a left bend on the fault, and the bend and the fault then continues basically. What's that? Okay, then sorry. Then we have southwest northeast trending faults again. The area was being compressed and created folds, and those folds folded up the sandstone that were placed inside the basin before. These would have been the Nariva turbidites. So those turbidites were placed. We then folded up the area, and as we folded the area, we then it was then covered with layers and layers of clay as well. Following that, later into the Pleistocene, about 5 million years ago, if the stress regime of the area changed. So no longer are we like compressing it from the north, we're actually pushing it relatively from the west to the east. And what that allows is that at this bend is then going to be under a lot of strain, right? And so locally, that basically creates a pop-up flower structure in this area, which leads to higher pressure or overpressure of the reservoirs. The reservoirs in this area are the Mariba sandstones. They're being charged with hydrocarbons as well. And you put all of that into the mix, you end up with a mud volcano. So as those faults break up towards the surface, fluid comes to surface, and the fluid carries the mud up, and it then leads to a mud volcano eruption. These are some seismic tomography lines that was acquired by UE across the mud volcano, and they were acquired at different dates. So this was in 2018, 2019, and after a significant earthquake in later 2019. And what we're seeing here is basically the warmer areas are the areas where we have the sandstones charged with fresh water, and the blue areas or cool areas are where the fault is coming up for the mud volcano itself. And so what you see happen over time is that sometimes the aperture or the throat of that fault or of that one volcano moves or squeezes over time. And sometimes that leads to a burst in activity. All right, now moving further south, here's a line across southern basin Trinidad. Obviously not as pretty as some of these seismic that we had before, but you can still make out a few features. There are some folds here, nice declines buried below the ground. And then we have like some broad bowl shaped features like synclines, okay? So here's our deltaic sitting in the synclines. And then down here we have older rocks, which are usually deep water turbidites deposited within these folds. So those red lines are faults, thrust faults in most cases. And so those thrusts are creating the formation of these folds. And in some cases, you see these green layers. That's the Carrera or mid-Miocene age rocks. And they're being folded and also back thrusted and sometimes even repeated over each other. There's even a recumbent fold occurring over here below the penile bar area. Sitting above that is pretty much an undisturbed syncline, right? So none of these rocks are folded, very much forming that nice fold. A lot of the folding occurred before, and then you got buried under the syncline. Jumping over to the Pitch Lake. So here's a group that would have taken out to the Pitch Lake. It's the largest natural man-made, largest natural asphalt deposit in the world, a natural seep. And so what's going on below this area is that we have the Cretaceous rocks, which are the rocks that expel the hydrocarbon. They're actually closer to the surface than normal. This is one area where they're quite shallow, right? They're still sitting at about 5,000 feet below the ground, but they're also stacked up. It's not just one layer of them, it's multiple layers of them. And so that allows for a lot of hydrocarbon generation, right? As those hydrocarbons are generated and they move upwards in the stratigraphy, sitting above those rocks, rocks that you see the sort of jagged sort of nature to it. And even in this case, it's sort of dashed line to it. What's going on there is that those rocks actually got exposed at some point, and a lot of erosion occurred. So we have an unconformity occurring in this area. And so because of that unconformity, this area got exposed, eroded, and a lot of sediment not occurring in this area because it was land at that point in time. Areas further to the south would have had more deposition than this area sitting below the pitch lake. So because of that, we have less deposits on top of the rocks that would generate the hydrocarbon and expel it. And so the hydrocarbon has a greater chance of actually seeping up the surface. And most of the rocks that sit on top here are not necessarily rich in clay. There are a lot of sands. And so the oil basically goes into some of those sands, does not have a significant clay to cause a trap, and it continues to leak upwards. And that's how we have the pitch lake occurring. And jumping to the east, now we're in the southeastern part of Trinidad in a place called Guayaguyare. We have a feature called the Salt Spring. Salt Spring was noted on Kugler's 1959 surface geology map. But the word spring might be a bit misleading. You might think that, well, it's gotta be like water that's being derived from somewhere higher up on hills or something, coming downwards and being expelled naturally, right? Based on gravitational flow. In this case, this is actually a clearing in the forest. So here we have some hikers hiking through the forest. It's thick forest everywhere else, and all of a sudden you see daylight. You see a very much clear ground surface. The ground is actually covered in limestone, and it's a hill, and water is coming out and flowing at the top of this hill, and flowing and cascading down the hill. This water is not fresh water, it's actually salt water. It contains hydrocarbons, and it also is very hot. It's 40 degrees Celsius. Right, so we have geothermally heated water coming out of the ground. It's salty as well. It's cascading down the slope. But where does the limestone come in? The water is also rich in calcium carbonate. And so as it flows downhill, it precipitates the calcium carbonate as tufa. And so we have evidence that in a nearby well, there were limestones encountered. So it's telling us that deeper in the ground, there are limestones in this area. And that limestone is being dissolved into the salt water, it's being expelled along this salt spring fault at the salt spring area. And then that's leading to the deposit of tufa at surface. Right, I think this might be the last spot. We're looking at the coal beds sitting out in the Mayaro area. So there are a couple areas on the east coast. It's even on the Caroni Basin side where we have coal mine. And then coming down here into the Mayaro area where we have coals occurring as deposits. Sitting below the coals, students here would have been looking at some of the white layers, which are sandstones. And those are nice shallow marine sandstones. But sitting on top of that are lignitic muds and then lignites. Lignites are essentially preserved trees, branches, leaves, any sort of very rich carbonaceous material, right? These deposits basically usually occur in swampy conditions. So low oxygen conditions, so it allows the preservation of these materials. So the carbon doesn't break down. And interestingly, in this particular outcrop, you can even see tree roots in place, so in growth position as well. So at one point in time, you would have had shallow seas across this area. Then there was a significant drop in sea level, and the sea basically moved eastward, and the mangrove moved onto the area that was the shallow sea. So that's what occurs here. In between this, you get the yellow bands, which are full of sulfur, which occurred because of the reducing environment. Los Iros. So at Los Iros, we would have had a significant amount of faulting and land slippage after that earthquake that we would have had. Just to put some scale on it, here's a tractor, and that's one of the faults, right? Pretty significant amount of slippage there. In this case, all of the slippage is pretty much from here downwards, right? But along the road area over here, you can see that it's not simply just that. This area actually moved quite a lot sinistrally, right? So we have people for scale over here. That's a pretty big break in your road. We zoom out a bit. So we were just up over here looking at that tractor. What happened when the air slipped? You get like the whole coastline basically being pushed up, forming like tow truss, lifting the sand on the beach up, causing a series of ridges. Have some people for scale as well. The sand is lifted up and undisturbed. Um, literally being lifted up as the rocks below lift up, and they're still sitting as if it was normal deposited beach sand. Here's some drone imagery of the whole area. It showed that a lot of the area actually slipped downward and basically pushed the coastline outward 106 meters. The blue outline was the original coastline of Trinidad. And that fault breaks the road, and it breaks a whole series of roads as well too. So we'll go and look at one of these breaks up here a little bit. So yeah, in a in a in a in a landslide, you would normally have a scar, a head scar, sinistral motion on one side and dextral motion on the other side, right? And that occurs relatively over this particular area. What goes on up here is a bit different. Over time, we also saw with doing multiple drone surveys, the area that was unstable, this area, continued to slip. So you can actually see the growth of the throw on those faults over time. So we've done surveys, weekly surveys, and see how the faults were growing, which faults were still active and which were not. And so the faults that were further up were not active anymore. The area that was unstable kept slipping. And that's us sitting on some of the small faults just for scale there. And further up where the fault basically shows more of a strike set of motion. Very clean cut, very sharp break there. You could even see some of the farmer crops and the lines from the farming crops there, completely offset from those lines further to the south there. That area over time gave rise to some new mud volcanoes forming. And so mud basically was coming up old tear fault in the area and bringing some very old material from thousands of feet down upwards over time. So those muds were sampled and we saw ages of from the early to mid Miocene from those muds. Okay, so here is where Trinidad sits, and here's where Tobago sits today. Like I said, we use that fancy word allochthonous. They're very far traveled. They came a long way, right? And how did it sort of like piece together over time, right? So we're gonna just break Trinidad apart into the different components and Tobago, and then move it through time. Right. So here's about 65 million years ago. 65 million years ago, the brown areas is the South American continent, and the blue area is basically ocean, right? And obviously, as you go from the continent to the ocean, it gets deeper. So you have deep water conditions occurring out here and shallow water conditions occurring here. So at this point in time, we would have been depositing in the Northern Range area, the rocks that would become the Northern Range. We would have had mostly those limestones, the quarry limestones being deposited here. That would then later help us form Turin. So that was happening at this point in time. Much of Trinidad was under very deep water conditions. 34 million years ago, Tobago would have emerged. Its sister island may have been emerged as well too. So they would have been volcanic islands, both volcanic islands. They're out of the water, and volcanism might have at this point in time begin to stop, and the islands basically begin to erode over time as they're out of the water. Meanwhile, the rest of Trinidad is still under deep water conditions. The Salt Spring area to the south, on the southernmost part of Trinidad near Guayaguyare, may have been uplifted at this point in time. And that may have actually been one of the first parts of Trinidad to actually become land. Okay? Following this, now 25 million years ago, we begin to uplift the northern range. So that part of it becomes land. The Caroni Basin is still underwater. Central Range is still underwater. We're putting actually our river sandstones in here that would later help us form the Paro mud volcano. And so those sandstones are being deposited inside here in the low areas. The Guayaguyare area is actually still sitting out of the water as a sort of island by itself. By 12 million years ago, we lift up most of the northern range and the central range, Caroni Basin area. Tobago and its sister island are moving along, coming along with us. Both are out of the water still. A lot of the central range gets lifted up in the fold belt because now we're compressing the area because of the bulldozer from the Caribbean plate. The Guayaguyare area is still sitting out of the water. And there's a seaway between the central range and the southern Trinidad, right? At this point in time, we would have been depositing the Herrera sandstones at mid-Miocene time into this area. So we don't really expect the Herrera to be further north of here, as this area would have been land at this point in time. Then at about 6 million years ago, the western northern range begins to go down. The Gulf of Paria starts to expand. And as that expands, it drowns the western side of Trinidad and it uplifts the eastern side of Trinidad. Tobago and its sister are still moving along. They've passed us, right? And its sister starts to drown. So the North Tobago fault starts to kick in and it starts to go down. Folding continued in the central range, so more and more area began to be lifted up and get lifted up out of the water. And the Salt Spring area actually momentarily goes down, allowing some of the deltaics to be deposited on top of it. So these are the last days of deep water deposition in southern basin Trinidad, with the lower cruise being one of those last sort of deposits. Hydrocarbon would have started to generate at this point in time due to a significant amount of loading from the deltaics onto the source rock. And so some of the seeps that would eventually form like the pitch lake starts to form at this time. And then by 2 million years ago, the delta is now building out to the south of us, very similar to like today. Strike slip motion kicks in more significantly now in the central range, which allows the river sandstones to expel water and hydrocarbon upward and create the localized compressional structure for the Piparo mud volcano. Salt Spring is emerged, and maybe that at this point in time, the fault starts to leak hydrocarbons and water to the surface. We start to form these tufa deposits now. The coaly beds are being laid down on the east coast of Trinidad as the delta moves back and forth across Trinidad. Drastic drops in sea level, drastic rises in sea level due to glaciation. And we have biogenic gas accumulating inside the deltaics on the north coast area. Right. And that is my story for the evolution of Trinidad and Tobago and a little bit about the geography and geology of it. So, any questions? Let me see in the chat. Okay, so I see, how recent is the magnetics map and does it match trends shown in the gravity maps? So that magnetics map was acquired in the late 1990s. And how does it match the trend shown in the gravity map? It I'm not 100% sure. It does seem to match quite a lot, but I know there are some newer ones, right? And the newer ones have higher resolution to them. But generally, the southwest northeast structures are still there, right? In the case of the hibiscus field, is that in Naprima Hill source rock? Is that in Naprima Hill source rock does not exist there? Yes. So when you drill into that area, the wells have been drilled all the way down to the basement, and they found the metamorphosed basement. And the metamorphosed basement is usually Cretaceous in age. And so that is related, more related to the rocks that are associated with Tobago, right? Where those are Cretaceous age volcanic and metavolcanic rocks. Quite a lot from this. The the drainage pattern observed in the basement of Tobago suggests that during time of deposition of the source rock, during the Cretaceous, the Greater Tobago area was either terrestrial or very shallow water. Is this why there's little to no source rock in the area? Um, no. So the Cretaceous volcanic rocks in Tobago and offshore Tobago were uplifted. And like I said, they were uplifted since, just shortly after the Cretaceous. Um, and so they were eroded over time, right? Um, they were volcanic at the time when source rock was being deposited in other parts of Trinidad. Okay. Since the North Coast expresses a general stepwise structure and the dragon to orchid fields lie along a structural height, would there be other fields further out but deeper below the sea level along other bands of structural heights? Yes, for sure. So even as you go further east of Orchid, there's the Castro field, which is similar, is on that structural high, which was the Isla de la Asunción Island, being the high there. And then even further east of that, the settling in the area, there was another gas discovery out there called Sancoche. And beyond that, there are other structural highs as well too. So in that area, all you really need to find, well, not all you need to find, but like a very quick way to narrow down some gas deposits, potential gas deposits would be to map the basement. Find the basement highs because as basement is a very different type of rock compared to the softer feldspathics above. So as the softer feldspathics compact onto the harder basement, you naturally form anticlines. So yes, so map your basement highs and then look up of that. Most likely you'll find some bright stuff inside the there. Um uh yeah, good. I know that in one of the areas that they're also promoting a lot of work right now is the area between Tobago and Grenada, right? So that's another area with lots of potential. Let's see. What happened to Naparima Hill in the Caroni Basin? So the Caroni Basin would have come up, and a lot of it is expected that if there was Naparima Hill, please say it may have been eroded or not deposited. It's a dual argument there. They're very a bit difficult to prove. Most wells that have been drilled there, they did not encounter the Naparima Hill formation. We have limestone caves such as Gaspery. If Gaspery has similar geology to the rest of the Northern Range, why don't we have more caves like that on the mainland? So we do have limestones and we have small limestone caves throughout the northern range, right? The rocks that form gas-free are on the southern side of the northern range. And some of those rocks, when you come onto the mainland or Trinidad, right, some of those rocks are actually below the deltaics. So the deltaics actually filled up and cover some of those, right? Um, I think I covered all there. And comment on Patos Island geology. Yeah, Patos Island geology. Just looking at my surface geology map here, it actually has the same geology as it shares the same geology as Gaspery Island, which is the same age of rock that you expect to have in the Belmont area and areas all the way up to like Tunapuna, those same style of rocks, right? So those are of the, let me see, this is the, right. So they're the Galera and yeah, so the Galera age rocks. Similar age to like what's out at Galera as well too. So Patos should have, I haven't been, but they should have very similar style geology over there as well. So what you see on Gas Spring. Hmm. Yeah, time. All right. Okay, folks. So I think we'll wrap up there. Again, thanks for coming out. Stay tuned for more of the stuff from SB with respect to the Mature Basin Symposium, right? And yeah, so look out for that technical program dropping next week. And yeah, hope to see most of you all out there. This would be a really good a good symposium, good talks and panels and stuff. Okay. Thanks so much.